3, B and N are constant. Okay, we look at B and N are constant. So now, if we were to draw a stress strain curve, so now we are focusing on the function now. Okay. So if this is 300, this is 600, and this is 900. Okay. Because B and N are constant, this is our graph. Okay. And then I'm going to plot this and plot this now. Okay. So this over here is for material number 1. Over here, material number what? 2. Over here, material number what? 3. Okay. So you can see if the A value, right, in the expression increases, you can see how the stress strain curve what? Shift. Right? So for this reason, when I sketch, I'll let you guys finish copying first. So for this reason, when I look at the numbers, right? When I look at dual phase steel numbers and I look at AI 1045, I start AISI 1045 at 553.1, right? I study over there. And then by looking at dual phase steel, the A value is what? At what? 120. Okay. And then the next component, okay, right? So the next one, we are going to focus on B, which is known as the strain hardening coefficient. And then N is the strain hardening index, right? So what if material 1, okay, you have B1 and N1. Material number 2, you have B2 and N2. Now, you have to look at both. You cannot decouple them. You cannot just say I leave N constant and I don't do anything or vary my B. No, they're all linked together, okay? And then material number 3, you have B3 and you have N3. And A1, A2, and A3 are equal to what? A. Okay, so the A, so I'll put down here, we also have A1, A2, and what? A3. But next condition I'm going to put is this, okay? So B1 is smaller than B2 is smaller than B3. N1 is smaller than N2 and is smaller than N3. Okay. So now if we were to sketch the stress strain curve, okay, we were to sketch the stress strain curve. Right? And it will look like this. This is for material number 1. This will be for material number 2. And this will be for material number what? 3. Okay. The difference between what we have done before, right, these three lines, they are all parallel to one another. Okay, whereas over here, the three lines are not parallel at all. Okay. Any questions so far from anyone? We okay with this? Okay. The next thing that we are going to do a short example. Okay. We are going to, I want you all to do this. We're going to find the elastic and plastic energy, right, to deform AISI 1045, okay, up to a strain of 1.0. Okay. So given the value, okay, we know A is equal to 553.1 times 10 to the power 6 Pascal. B is equal to what? B is equal to 600.8. And N is equal to 1.234. Okay. So if we look at U elastic, and we did the formula before, we have stress U squared divided by what? 2E. All right. And then we let the material, the Young's modulus is equal to 200 times 10 to the power 9. Okay. Yes. Oh, yeah. 1.234 is good. Thank you for letting me know. Any mistake that I make, you find out, you get a pint of beer. If you can't drink, orange juice. Okay? So we know, right, A is also equal to the what? U strength, yes or no? Right? So this is 553.1 times 10 to the power 6 squared divide by 2. And the Young's modulus is 200 times 10 to the power 9. So this will be equal to what? 553.1 power 6 squared, or 553.1 power 6 squared divide by 2, divide 200 power 9. What we have is equal to, I get 0.765 times 10 to the power 6 joule per what? Meter cube. Okay. The next one we are going to calculate is U plastic up to a strain of 1. So we work out the formula earlier is 553.1 times 10 to the power 6 multiplied by 1, right? Plus our B is equal to 600.8 times 10 to the power 6. Epsilon is 1. This will be equal to 1.234. And then the whole thing divided by 1.234. Okay. So this is equal to 553.1 power 6 plus 600.8 divided by 1.234. No. 553.1 power 6 plus 600.8 power 6 divided by 1.234. I get 1039 point 972 times 10 to the power 6 joules per meter cube. Right. So what you realize over here, right, is the U, the energy to deform the structure in the elastic is so much smaller than the U for what? Plastic, for a strain of 1. Okay. Right. Go for a 10 minutes break. We come back, we carry on. 10 minutes break.